Council.
I'm Matthew Zhang.
I'm Liza Kuzan.
And I'm Jeff Gao.
And our project was stroke rehabilitation through Android games. So this is an outline of what we're going to talk about. First, we'll give you some background on stroke rehabilitation. Then we'll talk about our research and results, and then we'll conclude with a few acknowledgements. So for a long time, doctors thought that the brain was a relatively static organ, so once it was injured, recovery was nearly impossible. But recently, this theory of neuroplasticity is becoming popular. The idea behind neuroplasticity is that the brain compensates for injury by allocating tasks usually performed by the damaged neurons to neurons that are used less frequently, and this results in new neural connections. Neuroplasticity can be induced through repetitive exercises, such as squeezing a stress ball or stretching a TheraBand. And one of the reasons stroke rehabilitation is so challenging is because therapists have to deal with a broad range of consequences, including cognitive, physical, and visual disabilities. Vascular dementia is a broad term used to categorize any disability caused by a reduced blood flow to the brain. In that image on the right there, you can see that the stroke patient has blood clots in their brain. And this can have a variety of side effects, including confusion, hallucinations, dizziness, difficulty focusing. Aphasia is the loss of ability to communicate either through written language or verbally. The physical effects of stroke are usually more dominant on half of the body because each half of the body is controlled by a different hemisphere of the brain. So the half of the body that's controlled by the damaged hemisphere usually has more evident physical effects. So hemiparesis is the weakening of half the body, and hemiplegia is the paralysis of half the body. Spasticity is a condition where the patient loses the ability to grip or ungrip things. And all of these physical consequences can severely impair activities of daily living, also referred to as ADLs. And ADL is basically any activity that the patient performs on a daily basis, such as washing the dishes or driving a car. And stroke therapists often use ADLs as a way to measure patient progress. So in recent years, there's been a trend towards bilateral rehabilitation. Bilateral rehabilitation is popular because the patient can use the stronger half of their body to help the weaker half relearn motions. Some examples of wrist motions are flexion, extension, radial deviation, ulnar deviation, pronation, and supination. And these are the motions that our games focus on. This is the Dynawheel. It's a device recently developed by Dr. Crealis and Dr. Newberg here at Rutgers University. And as you can see, the Dynawheel has two triggers that the patient can grip, interchangeable stands, and most importantly, a smartphone mount. Smartphone integration has benefits for the patient, the facility, and the therapist. The patient has a more motivating rehab experience as they hopefully see their scores improve between session to session. The rehab facility gets to use the metrics produced by the smartphone to produce standardized reports, which can be used as evidence-based outcomes when they submit insurance claims, for example. The therapist gets more one-on-time with the patient because they don't have to spend hours filling out tedious paperwork. Smartphone integration also opens up doors for countless research opportunities because so much data can be collected by the applications.
Because the Dynawheel is a pretty new device, there's currently only one game available to be played. So our task was to develop a suite of Android games that can sync with the Dynawheel and be played on the Dynawheel. On a standard experimental setup, we would use real clients and test their progress over time and record their setup and track their progress in order to make sure the Dynawheel is functioning. But because we do not have the clients or the time, we instead tested for the usability of the Dynawheel, the usability of the apps, and we just wanted to increase the number of apps inside of the store. So we developed two apps, the Maze Race and the Veggie Catcher game. Now you might be wondering why we did not just download games from the Android store and just implement them in the Dynawheel. It's because we followed some specific game criteria to develop the games. So here's a list of the game criteria. The first criteria we had to follow was patient metrics. This is basically recording of several functions that the patient undergoes while playing the game. For example, measures maximum extension, maximum flexion, maximum radial, ulnar deviation, stuff like that. Also measures time and endurance. This is useful for the therapist because he can track the patient progress using graphs and also analyze statistics. It's useful for the patient because he can also track his day-by-day progress. The game also implements recovery ADLs. ADLs is on-set or activities of daily life. For example, eating, bathing, drinking, washing. or combing. So the games that we developed were based off ADLs. The Veggie Catcher game has a pretty tangible connection to this. It's a simulation of picking up fruits or vegetables and putting them into a basket. The Maze Race game is vaguely based off an activity daily life because it has the same motions as steering a vehicle. Both these games also implement wrist movements, which is pretty much just flexion, extension, radial, ulnar deviation. But there's a slight difference between the two games. The Veggie Catcher game is held in a horizontal position like in a lunch tray, and the Maze Race game is held vertically like a steering wheel. And this involves emphasis on different muscle groups. Both games also implement hand-eye coordination because as a stroke victim, you will lack the ability to actually concentrate and your reaction time will be increased. So the hand-eye coordination is basically you see what's on the screen and you react to it. And both games will have to train the hand-eye coordination. Also, both games have to be engaging but simple, and this is important in our graphics engineering process. We had to make sure that the background was monocolor, it lacked any background noise, we had to make sure that shapes were symmetrical and easy to see. We had to keep emphasis on the objects inside of the game and move everything else to the side. And it also has to be engaging, so we also had some color contrast so the patient would easily focus on what is at his hand. We also had to take in mind cognitive functionality. All these previous things were just physical impairments, but this is cognitive, which means you lack focus, you cannot concentrate. So all these games will have to improve that, and also has to be suitable for recovering patients because stroke patients, they have different symptoms and they vary based on the location and the severeness of the stroke. So we had to develop customizable settings in each game that is suitable for each patient.
The application programming interface used to develop the games is Gyroscope with the programming language Lua. It features a Wi-Fi-based debugger and allows for cross-platform development. However, the debugger is ineffective in areas of weak wireless signal, so Java may be considered for solely Android development in the future.
So these were the Android sensors we implemented in our game. We used the gyroscope and accelerometer. We'll talk later in detail about these two devices, but instead of using just one device, we decided to use two to test the potential of the Dynawheel implementing both of these features. And the important difference is that gyroscope measures angular velocity and then integrates that to get the position. The accelerometer measures the acceleration and integrates it twice to get the position. But because the accelerometer is affected by outside forces, it must be held horizontally because gravity takes into account in the objects in the game. We also use the magnetometer, which is essentially in the phone's compass, and it detects changes in the magnetic fields. This is useful for the Dynawheel spring complex system because when you squeeze the spring, there's two magnets on it, and that will change the magnetic field, and the phone can detect that.
The gyroscope sensor was used to control the character in the maze game. So theta y is the angle of rotation about the y-axis of the phone, and theta z is the angle of rotation about the z-axis in radians. These values were approximated programmatically by integrating the rates of rotation acquired by the phone's gyroscope sensor, and the velocities of the characters the character was calculated by these formulas. The x velocity has a negative sign just to correct for the direction of the character moving on the screen, and the maximum speed is 12 for the games. It's just a constant.
So this is the basic concept of accelerometer. As you can see on the left, the accelerometer is basically a housing with a mass inside of the house, and pretty much the mass moves based on external forces, and the housing will detect those movements and later translate those movements into acceleration. On a phone, it's a little bit different. There's a housing and a silicon comb, and as the silicon comb moves, it's essentially a differential capacitor, and it changes the current, and the phone translates the change in currents to acceleration. As you can see on the right, this is what accelerometer usually measures, and because it's based on a silicon comb, it varies in frequency really constantly, and it shifts. This will be impossible to actually implement in the game because even at rest, the figure in the game will move constantly. So we had to implement a low-pass filter that essentially smooths out the accelerometer values, and a low-pass filter is pretty much an exponential moving average. It weights the current values greater than past values. As you can see in this recursive formula, you have an initial value, and then every value subsequent to that initial value, you weight it. A is the constant that's filtered from 0 to 1. 1 is essentially no filtering because you're just using all of the new value. 0 is essentially nothing. And lower values, it smooths it out more, but it also increases the delay time in the movement of the phone and the sprite change in position. And this was important to our game because it also allowed us to affect the speed of the player. By using lower filter values, it would be suitable for patients with low hand-eye coordination and low reaction time because they have more time to react to the changes in the sprite, although the sprite will actually be slower. If we increase the filter value, if we increase the A value, the sprite will be faster, but the patient will also have to have a greater reaction time and be able to react more quickly.
In designing the games, we have to take into account player limitations because the targeted audience has cognitive impairments and a limited range of motion, especially in early stages of rehabilitation. Working with a smartphone also meant that we had to design and develop for a small display screen, processor limitations, and inherent sensor inaccuracy. It was also important to minimize patient interaction with the touchscreen because stroke patients have difficulty operating a small interface. And the most important part for the actual gameplay was to use repetitive wrist motions while still making the game engaging and interactive.
Okay, this is the simulation of the game. Because we did not have the Dynawheel at hand while we took the video, this is an emulator based on the Gyros player. So right now we're playing the game, and on the right is a magnetometer. It's a simulated magnetometer. It's not actually the squeeze system, but that simulates the squeeze. This is the calibration. It's suitable for every patient. So every patient, when they squeeze it, you can record the maximum values. So the Dynawheel will be implemented for every single patient. As you can see, we have customizable settings on there. There's 4 different options. You can turn the grip on and off because some patients cannot actually squeeze it. We have a reset button, and we have a time for game and speed. There's a total of 32 different customizable features. The time goes from 30, 60, 120 to 180 seconds. There's a fast and slow speed. There's a reset on and off, and there's a grip on and off. So pretty much when you start the game, you tilt the phone to move the hand onto the vegetable. And because the grip is on, you have to squeeze the grip to grab onto the vegetable. You have to drag the hand over the basket, and then you have to release the magnetometer to actually release the vegetable. The vegetable resets and changes colors if you score a point. Because the reset is off, if you release the vegetable not on the basket, it will not reset back on the top, but it will only reset if you place it right on the basket. This is suitable for patients who lack motor control, and it's easier for them to actually score. Now, if we turn the reset on and we turn the grip off, you will see that we don't need to actually squeeze the magnetometer to grab onto the fruit. Instead, all you have to do is drag the hand onto the vegetable and then bring it down. Because the reset is on, if you drag it off to the side, the vegetable will reset. You won't score any points, and the vegetable stays the same color. It will only score points if you actually drag it inside of the basket.
The maze game uses the gyroscope sensor to control the character's velocity, as explained before. The goal of the game is to get from the starting location to the finish line, and the velocity controls were used rather than position because patients with a limited range of motion would still be able to complete the game even if they could not move their wrists completely side to side or front and back. And as the patient's range of motion increases, the time will improve, their score will improve, and that will reflect their rehabilitation improvement.
So after we finished developing our games, we performed clinical trials at the JFK Rehab Institute. We tested the maze race game on a male stroke patient in his 50s who had a stroke about 3 months ago. This patient, obviously, his movement was obviously affected by the stroke as he couldn't freely move his arms, his hands, or his wrists. For example, the patient was able to grab things, but after he grabs them, he had trouble releasing them. In addition, as with typical stroke patients, one side of his body was affected more than the other. his left side was the weaker side, but his right side was also slightly affected. The patient also had a slight limp in his walk, and he walked slowly. So due to the short amount of time, we tested our games for the usability rather than the effectiveness. So overall, for the maze race, it functioned pretty well, and the patient enjoyed playing our game. The patient was able to maneuver the player through the 5 different courses and finish the game. It took him 57 seconds bilateral and 64 seconds unilateral to finish the maze race game. But the therapist also noted a few issues with our game. One issue was that the patient depended heavily on his stronger side, and also sometimes the patient depended on trunk movements rather than actually exercising his hands and his arms and his wrists. The therapist also advised for us to add more customization options. As you saw with our veggie catcher game, the therapist is able to have the option to turn the grip on and off, set the time limit, also have the option to make the game more difficult by turning on the reset option. The therapist also advised to add more patient metrics so we can measure the improvement of the patients. So just to conclude and sum things up, the goal of our project was to create 2 Android games that can be used with the Dynawheel to provide a fun way to rehab and restore important functions of stroke patients. So as you can see, we created the veggie catcher game on the left and the maze screen on the right. We tested these games at the clinic, and overall they were pretty usable for the patient. So as I mentioned earlier, we only had a short amount of time, so we tested for usability. So the next step is to test for the effectiveness and perform further clinical trials so we could track the improvement of a patient over a few months. And another step we would do is to add facial recognition to fix a problem with the trunk movements. This would detect the patient's face and see if the eyes change, so it will know if the patient is using trunk movements rather than actually exercising his arms. We will also improve metric recording, enhance graphics, and add more customization options. Finally, we will launch our games and hopefully they will help patients in the future.
We want to acknowledge the following people for helping us with our project: Dr. Bill Kralis and Dr. Nikki Newberg for providing us with expert guidance, Colin Kosinski for helping us perform our clinical trials, Ravon Suffer for mentoring us and guiding us through the process, the JFK Rehab Clinic for allowing us to perform trials there, Neha Desai, our RTA, who made sure we were on track and focused, and John Patrick Antoine and Eileen Rosen for making the GSET program possible. We would also like to thank the following sponsors, without whom this project would have been impossible: Rutgers, Morgan Stanley, NJ Resources, South Jersey Industries, PSE&G, and the GSET alumni community. Any questions?
Is there an option that the patients could have this on their phone and they could use it at home also to continue their rehab?
Yeah, that's one of the things we were actually keeping in mind as we were designing the games. The great thing about the Dynawheel is that it's low tech, so it's very affordable. So it's possible for a patient to just have a device at home and play the games on their own phones. And we could eventually also add functionality so that the patient's results can automatically be emailed to their therapist. Yep.
You were talking about how ideally you'd like to put in more ways to customize the games. Is there any thought in the real Dynawheel or within your group towards using the kind of like accelerometer reaction time adjustment that you're talking about to kind of create levels in the game so that as the patient improved, you could like make it harder and force them to react faster? Is that something that's being thought about?
That was the purpose of the fast and that was the purpose of the speed button. Right now it only goes fast and slow. The slow button has a filter of 0.4 and the fast one has a filter of 0.9. It's possible for a scrollable feature, but that can be implemented later.
Is the Dynawheel connected to the smartphone? And how?
There's a mount on the Dynawheel that can mount the smartphone, but it's not physically or electronically connected to it.
How does the smartphone receive like the grip signal from the Dynawheel?
There's a spring. The grip is attached to a spring and there's a magnet on the end of the spring. So as you squeeze the grip, the magnetic field changes and the phone can detect the change in the magnetometer. And the original designers of the Dynawheel already implemented that system where they convert the change in magnetic field to the amount of grip.
So there's no actual data transfer going on from the Dynawheel into the...
The whole thing is non-electronic.
Yes, the Dynawheel is
Yes.
completely electronic. The games are all based on the sensors within the smartphone itself. So the smartphone is what collects all the patient metrics.
I believe it's all technical.